I'm Dr. Jacob Spies, 2022 Arnold Beckman Postdoctoral Fellow in Chemical Instrumentation. I'm currently working in the Department of Chemistry at the University of California, Berkeley in Professor Michael Zurch's group, where my research focuses on the development of new tools in ultrafast nonlinear spectroscopy to study the electronic properties of solids. So pretty much all of my research over the past decade or so has focused on solutions to the energy crisis in some form or another. As an undergraduate and graduate student, I focused on addressing this problem from the perspective of renewable energy conversion by studying how electrons move in solar materials. So when you shine light on a solar panel, the photons that make up that light excite electrons and generate a charge-separated state that can be harvested to either generate electricity or drive a reaction to make a chemical fuel. The ultimate goal, of course, being to ensure a future powered by sustainable energy that keeps our environment clean, kind of like the one in this AI-generated video. However, this little AI-generated clip, while convenient and cool, poses another problem. Beyond the ethical implications of AI, energy consumption from data centers is a significant concern. So even if we're able to develop new technologies for sustainable energy, it might not be enough to keep up with rising demand. Fortunately, we can also attack this problem from the perspective of data centers as well by developing more energy-efficient electronics, which has been the focus of my postdoctoral work. In particular, we're interested in studying how strong correlations in a class of materials called quantum materials might be able to enable these new devices. As a spectroscopist, I'm interested in how light-matter interactions can help us develop a fundamental understanding of the material properties that enable applications in energy. One of the implications of quantum mechanics is that molecules have these discretized energy levels like rungs on a ladder that can only hold 2 electrons each. The energy levels provide a fingerprint for a particular molecule and can be studied using light absorption to probe the energy spacing between occupied and unoccupied states. Dr. Beckman really revolutionized optical absorption spectroscopy with the invention of the DU spectrophotometer, making these kinds of studies widely accessible in the chemistry community and beyond. Overall, Dr. Beckman's commitment to developing instrumentation that is both powerful as an analytical tool and usable by non-specialists has been a big inspiration for how I approach spectroscopy and the design of scientific instruments. So now, when we go into the solid state, we've got a lot more interacting electrons, so those energy levels blur into these delocalized states that we call bands. In periodic solids, we don't really care very much about where the electrons are, since they're indistinguishable, but rather their momentum or how fast they are moving at a given energy level. This is shown as a band dispersion, where the shape tells us about interactions between orbitals in the solid and the conductivity of the material. However, probing band dispersions experimentally is quite challenging and typically relies on photoemission-based techniques that require very clean vacuum environments, ultimately limiting the systems that can be studied. My research as an Arnold Beckman Postdoctoral Fellow in Chemical Instrumentation has focused on the development of a technique called solid-state high harmonic generation spectroscopy, or SHHG for short, as a new all-optical tool to study the electronic structure in solids. In SHHG, we use a strong field ultrafast mid-infrared pulse to coherently drive electron trajectories in the solid, resulting in the emission of higher-order multiples or harmonics of that driving frequency. Because these coherently driven electrons feel the electrostatic environment of the material, information on the electronic structure is imprinted in that emission spectrum. One of the things that's really quite exciting about SHHG is that it is an all-optical method, meaning that it is amenable to a variety of different complex sample environments, ranging from electrochemical cells to diamond anvil cells for measurements under extreme pressure. In some recent work led by one of my graduate student mentees, Bailey Nevgen, we were able to use solid-state high harmonic generation to probe a previously unobserved isostructural electronic phase transition in MOS2, a 2D material, under high pressure in a diamond anvil cell. This is quite exciting because diamond anvil cells are a notoriously challenging environment to work with, and our work really nicely showcases the advantages of SHHG as an all-optical probe with extreme sensitivity to small changes in electronic structure. The support of the Arnold and Mabel Beckman Foundation has really enabled me to focus on developing new instrumentation for SHHG that has the potential to make some significant impacts in the chemistry and material science world. So in that regard, I think that this kind of high-risk, high-reward research really embodies the goals of the Arnold and Mabel Beckman Foundation, as well as Dr. Beckman's legacy in the fearless pursuit of scientific innovation through the development of cutting-edge instrumentation. I've been fortunate to work with a team of extremely talented students from the initial design stage using CAD to fabricating parts in the student machine shop here in the College of Chemistry at Berkeley to the process of actually building the instrumentation in the laser laboratory. So not only was I able to gain the technical skills required to be an innovator in spectroscopy, but also the leadership skills and mentorship that will enable me to train the next generation of scientists. As a physical chemist, when I think about what's next in the world of spectroscopy, I tend to look for inspiration in methods that are considered state-of-the-art in other disciplines and try to figure out how they might be applied to questions in chemistry. SHHG is a really great example of this because it's a technique that was born in the world of condensed matter physics and attosecond science, but it really hasn't yet lived up to its full potential in the context of materials chemistry. Real systems in chemistry are notoriously messy and filled with defects, and often these defects and heterogeneity are the drivers for chemical reactivity. So in my opinion, microscopy is the frontier in any developing spectroscopic method because you need to be able to look at these nanoscale features that drive reactivity under operating conditions. So once again, we can look for inspiration from other disciplines, but this time from our friends in biology and neuroscience who have figured out countless different strategies to improve the spatial resolution in microscopy beyond the diffraction limit. In my independent career, I plan to apply these same strategies to enable super resolution solid-state high harmonic generation microscopy that will allow us to image the electronic structure of materials in the complex environments where chemistry occurs.